Remind you what we'd begun to discuss in the last class. We'd begun to discuss the following theory. We'd begun to discuss a theory whose gauge group was SU2. The content of the theory was one gauge multiplet and one chiral multiplet. Okay, the gauge multiplet was gauge multiplet, and the chiral multiplet was in the adjoint of the gauge group. Okay, this theory was anomaly free. Didn't have a gauge anomaly, okay, and of a form gauge. That kind of anomaly was absent. And the matter content of this theory, there was a gauge field. There was the superpartner of the gauge field, which the n equals 1 superpartner of the gauge field, which was lambda alpha, the gaugino. And then there was also a matter field, this matter field, and its superpartner, which we call psi. And then when we wrote out the Lagrangian of this theory in components, we found a sort of interesting surprise. The surprise was that there was an SU2 symmetry. There was an SU2 symmetry that acted on so we wrote lambda alpha and equals chi alpha 1 and psi alpha is equal to chi alpha 2. And then we wrote under the transformation chi I is equal to mij chi j, where M was an SU2 matrix. Okay, this was a symmetry of the theory. Okay, there was another, classically speaking, there was another symmetry of the theory, which was a U1 symmetry, and that U1 symmetry was just the symmetry of phasing the field phi. So phi equals to e to the power alpha phi. Okay, and then what we did was to notice that if we acted on, if we combined one of these SU2 symmetries, the one which acted on psi and phi, like psi goes to e to the power minus I alpha psi, lambda goes to e to the power I alpha lambda. This was clearly SU2 because it's block diagonal and its determinant is 1. Okay, and we combined this with phi goes to e to the power 2I alpha phi. This was the full supermultiplet. So sorry, this was the full let me write supermultiplet with these fancy lines here, and scalar field without those fancy lines. So the full scalar of supermultiplet goes. Okay, so it's a flavor.
This scalar part, right?
Here, no, it's a full supermultiplet, because it wouldn't be a symmetry otherwise. You said there's a flavor rotation symmetry, but the full supermultiplet is rotated because of the absence of the superpotential. And there was the old SU2 symmetry. Now this full thing, what it does is phi goes to e to the power 2I alpha phi, and psi goes to e to the power 2I alpha phi psi. That's the explanation of what this is. So we combine this with this. The net result was psi goes to e to the power I alpha psi, lambda goes to e to the power I alpha lambda, and phi not just the scalar part, not the full supermultiplet, so e to the power 2I alpha. Right? So it acted on the fermions to lift this SU2 to a U2, but it also had some action on the scalar part. Okay, and we discussed in the last class the reason that we discussed that the reason we were interested in this theory was that despite appearances from the way I've written it, this theory was actually invariant under a larger supersymmetry than n equals 1. It was invariant under n equals 2 supersymmetry, and we understood that by looking at the R charge. This R charge, this U2 R charge, was the R symmetry of an SU2 algebra. Right? Classically, this is what we had with this theory. Remember, all clear? Good. Then we looked at these symmetries quantum mechanically. Okay? And we noticed that the non-abelian symmetries, this SU2, wherever I mean it, yeah, this SU2 was non-anomalous. As is often the case, right? Just because of the trace in the formula. However, the U1 was in general anomalous, and in fact we had d mu j mu is equal to some number times f wedge f by 32 pi square, and that some number was, now we are very good at computing, that some number came, well this anomaly came because each of these chiral fermions under this symmetry, so this is the symmetry we deal with. Okay. Each of these chiral fermions under the symmetry has charge 1, so there's a 1. Then there are two such chiral fermions, so there's 2, and then they're in the adjoint, so we get 2n. 2n, but n was 2, so that's 2. Right, so we got 8. So we got del mu j mu is equal to 8 into f wedge f 32. All good. I shouldn't write f wedge f, right? F wedge f is a 4 form. This is a scalar dual of that. All that, you know what I mean, right? It's, I should write epsilon mu nu alpha beta f. You know what I mean, right?
You mean trace of f wedge f?
Trace of f wedge f. Correct. Trace of f wedge f. Trace of f wedge. Trace.
What's the second two for?
Second 2 for, because there were 2 fermions. Right, first 2 for this. The formula was number of fermions, that's the degeneracy, into 2 NC, because we were dealing with adjoints. So the second 2 was this 2, and the third 2 was that NC was 2. Okay, so I'm sorry for writing it messily, but you know what I mean. Okay, we concluded from this that this symmetry, this U1 symmetry, was broken down to Z8. We also realized that actually of this Z8, only Z4 was non-trivial, because a Z2 subgroup of this was already present in the SU2. That was the Z2 when we did this like 4 times. Okay, this was the Z2 when which took psi and lambda to minus themselves, and phi to itself. And this was an SU2 just because a 2 pi rotation with an S. You know, if you think of SU2 as a SO3, and then do a 2 pi rotation with an SO3, that acts on spinors with like a minus sign. Okay, so this Z8, but if you really, the full symmetry group was Z4 times SU2, right? Because Z2 of that Z8 was an SU2. Okay, excellent. There's a comment here that that I should have made last time, but let me make it this time. Okay, you know, classically, this theory here is defined by its coupling, by among other things, its coupling constant. The coupling constant tau that comes behind when we write imaginary of tau W alpha. And that coupling constant tau had 1 over g squared plus I times theta. Had a real part and an imaginary part. Okay, quantum mechanically we actually see that there is a sense in which theta is not part of the definition of the theory. Okay, why do we see that? We see that because, you see, this is true whenever we have an anomalous symmetry. You see, a symmetry that's not anomalous allows you to make a change of variable without changing the action. In a symmetry that's anomalous, you can still make the change of variables, but the price you pay is that you change the action. Okay, so suppose we look at this symmetry here. This symmetry labeled by e to the power I alpha and all of this. We make the symmetry transformation inside the path integral. Okay, the fact that it's anomalous tells us that the measure in the path integral is not left invariant under this change of variables, but changes. And it changes by action. So the measure is e to the power is. Right? So it's or minus s in Euclidean space. Okay, and it changes by s goes to s times f wedge f by 32 pi square times 8, that 8 was here, times alpha. Okay? Now, the fact that when we let alpha vary from 0 to 2 pi by 8, we can generate any value of theta we want. Okay, so I start with a theory with any value of theta you provide for me. Then I do a change of variables inside the path integral. That takes me back to the theory of the same form, but with theta set equal to 0. So there is a sense in which you can start with a theory with any value of theta you want, but relate its physics to the theory with no theta. So in that sense, the action here, this physics here, is actually independent of theta, because you can always choose variables in which you set the action to have theta equal 0. Is this clear? Okay, this is a familiar thing. It happens every time we have anomalous symmetries. You make the symmetry transformation. That's no longer a symmetry in your theory, so you've lost a symmetry. But what you've gained is the ability to move a coupling constant to wherever you want without changing physics. Is this clear? Let me say this one yet again. Okay, in a symmetry, you have one set of variables has the same dynamics, same correlation functions, as another set of variables. Because when you do the change of variables, the action in terms of the first set of variables is the same as the action in terms of the second variable. So any insertion you calculate in terms of the second variables will have the same answer as any insertion you can compute in the first set of variables. When you do a general change of variables, inside a path integral you can always do changes of variables, nobody can stop you. Inside any integral you can always do changes of variables, nobody can stop you. Okay? But a general change of variables has the property that it mauls the action. The action written in terms of the new variables is some crazy stuff. In particular, not the same in functional form as the action written in terms of the old variables. Okay? But these anomalous symmetries are sort of in between. They're things that don't preserve the action, but they change the action. So the action in terms of new variables is written in terms of the action in terms, is related to the action written in terms of old variables in a very simple way, just by shifting an effective coupling constant of a 4-derivative term. Okay? So what this change of variables does is relate any calculation you can do in the theory with theta to some calculation you can do in a theory with theta equals 0. You know, symmetry would relate any calculation of some set of variables to the same calculation for another set of variables in the same theory. Here you're relating a calculation in one theory with a calculation in another theory, and thereby forming an equivalence of the class of theories rather than an equivalence of the class of calculations within a theory. Is this clear? So this often happens with anomalous transformations. What you get to do, instead of having the consequences of symmetry, is get to learn about other theories in terms of a standard theory. Is this clear? They will be different. But so you haven't learned it.
They must be related in some way.
No, not very much. You see, because the original variables, if we perform the new variables without changing theta, that is not a symmetry of the path integral. Okay? So new variables plus new theta gives you same answer as old variables plus old theta. Okay? So the thing is not a symmetry. But what you've gained is to say that any calculation I can do in this theory is equivalent to calculation I can do in this other theory. Okay? This is always true of changes of variables. The important thing here is that new action is a very simple one. I mean, it's not some crazy thing which we weren't interested in studying. Okay? So, fine. Okay, so in this theory, even though classically theta is a parameter, quantum mechanically there is a sense in which theta is not a parameter. The sense that you can always choose do a field redefinition to get rid of theta. Okay? We will not, so you will see we will sometimes keep theta, sometimes not, depending on taste. Because we can get away without thinking too much about theta. Is this clear?
In the non-anomalous theories, we cannot get rid of it.
You cannot get rid of it. So when n equals 4 Yang-Mills theory, for instance, where there's no anomalous symmetry, theta is a genuine parameter of the theory. The physics at one value of theta is different from physics at another value of theta. In standard model you cannot get rid of theta. Yeah, so now there is a complicated story there.
So if you can get rid of theta, then it's a symmetry and you are calling it as
Yeah.
anomalous.
Yeah, there is, in the standard model you have to phase the fermions to get rid of theta, and that changes some phases in the mass terms. So there is a constant that you cannot get rid of, and we can call that theta. What? No, there is a U1 symmetry, namely see, had the standard model had really massless quarks, then we could get rid of theta in the standard model. Because there is this, of the S, let's say there were two massless quarks, then the U1 of the SU2, the chiral rotation, would have been an anomalous symmetry, and you would have been able to get rid of theta. Okay? In the standard model, though, the U1 was not even a classical symmetry. That whole U2 was not a classical symmetry because the quarks were not massless. Okay? So what we were doing is like approximations. So when we do this chiral rotation, we change two things. We change phases in the mass matrix, and we change theta. So we can do this rotation to deduce that things cannot depend on the phase of the, cannot change if we change the phase of the mass matrix and we change theta in a complicated way, in a correlated way. But if we just hold the mass matrix phase to be real, let's say, then physics will depend on theta. There is one parameter left over. Right? Okay? This would not have happened had in the standard model chiral symmetry been an actual symmetry of the Lagrangian. Because then by doing the symmetry we would have changed another parameter. The fact that we're changing the phase of the mass matrix was the statement that even classically chiral symmetry was not a symmetry of the Lagrangian. So when we do this rotation we change two things. The thing that we do classically and the thing that we do quantum mechanically. Okay? And we can correctly deduce that things cannot be a function of this coordinated change. But there is still one parameter, namely the relative thing, that it can be a function of. This is what people usually call theta in the standard model. I hope I said that right. My standard model is, but I think it sounds right. Yeah. Okay. Right. There's this beautiful chapter in this book, Aspects of Symmetry by Coleman, in which he talks about this U1 anomaly and its consequences. Read that chapter. Even I should read it. It's been long since I read it. Okay. He talks about its consequences for the standard model. He will say this and then he will say more. There's this puzzle about the ninth pion that he talks about, this eta particle. Anyway, you'll see, but it's very nice. Okay, excellent. So fine. So this was our setup, and this is what we started talking about last time. Any questions or comments about this? Okay. Now, the next thing we did was to look at the theory classically. Okay. The first thing we did, next thing we did was to look at the theory classically. And the first thing we did in this regard was to look at the potential of the theory. Classically, the potential was given by phi bar mod square. Okay? And we also realized that because of n equals 2 supersymmetry, this was purely from the d term. But we also realized that from n equals 2 supersymmetry, the superpotential of this theory, you could not generate. Superpotential is a very n equals 1 thing. Maybe n equals 2 will force you to generate some superpotential. We will see examples of that when we look at n equals 2 theories with matter. But you can't freely change the superpotential in n equals 2 theory. And in this case, the superpotential was just forced to be 0. Okay, that was a consequence of n equals 2 supersymmetry. So the fact that the superpotential was 0 classically meant it continued to be 0 quantum mechanically. Okay, this is a very simple consequence of just n equals 2 supersymmetry. Okay, now the fact that the superpotential is 0 means that the actual potential here, which depends on, if you remember, derivative of the superpotential, but then the indices contracted by the scalar potential. Actual potential might vary, but its zeros cannot change, because every time del W by del phi was 0, the actual potential would be 0, because schematically the potential was of the form del W by del phi, del phi I, del W phi j, Kij, mod, and this is bar, a complex conjugate. Okay, this can change, and in fact we will study it a little bit, the scalar potential. This is the difference for the n equals 2 case. We will have control over the scalar potential, as I will remind you of in a minute. But the important thing here was that if del W by del phi I is 0, sorry, what am I saying? In this case, W is just 0. Forget about it. I was saying this about the D term. In the D term also, this actual potential can depend on the details of the kinetic term that come outside the gauge piece. Again, that's something we will study. Okay? But the fact that if D is equal to 0, the potential is 0, is just always true. Because the potential began its life as D squared, and then you integrated it out. Okay? So the fact that the zeros of this potential are exact zeros of the full potential is just always true. Independent stuff we have not yet controlled. Was this clear? Sorry, I messed it up by first talking about the superpotential, which I shouldn't have since it was 0. But is this point clear? Yes. You see, when we, in class, what we did was to take the Lagrangian, trace W alpha plus phi e to the power minus v phi. Okay? And then we looked at this term. This is d4 theta, this is d2 theta. We looked at this term, we looked at this Lagrangian, and we integrated out, we wrote it out in components. We found that we had some component that was like d square. Then we had another linear component that was d times, in this case, coupling to this object phi bar. Okay? And then we integrated out the d square term to get the formula for the potential. This is what we did in class. Okay? Now, in class, we looked at a very simple kind of potential. We looked at the potential that was trace W alpha, without any matter dependence here, for instance. And we looked at the scalar potential here. That was just flat. Very simple kinetic term for the matter fields. Okay? Quantum mechanically, both of these things can get renormalized. What that can do is change this business here by multiplying it by something. Okay? And maybe change this business here. This change will come from here. Okay? Sorry, no, this change will come from here, and this change will come from here, because the d square came from here, and the coupling came from here. Okay? So you will get some complicated stuff that we have not yet managed to control. But no matter what happens, if this term is 0, what you get by completing the square will always be 0. Okay? And so that's the point, that the scalar potential that we're writing down here is not completely accurate, but its 0 is 100% accurate. Okay, so the zeros of the scalar potential are always at locations where phi and phi bar commute with each other. Is this clear? Okay, fine. Of course, we used similar ideas when we were talking about n equals 1 supersymmetry, though I might not have emphasized it so much. We looked at, we said that when we had a moduli space of vacua, that was a place where del W by del M was 0. Remember, with that, all we did was to use it to denote the moduli space, the zeros of that potential. Never actually learn what the potential is, because that needs the Kähler potential, which we couldn't control in the n equals 1. Is this clear? Okay, excellent. Fine. So we discussed that that this theory has a moduli space of vacua. That moduli space of vacua, at least classically, is parametrized by phi, but up to gauge rotations, phi can be diagonalized. So phi is equal to A0, 0 minus A. Right? So you can think of A parametrizing vacua, but this fixes gauge symmetry up to a permutation of eigenvalues. So A should be treated as equivalent to minus A. So A mod minus sign parameterizes vacua, or equivalently trace phi squared, which is equal to A squared parameterizes vacua. Okay, and trace phi squared is obviously gauge invariant, so we will use it as when we need a specific coordinate, we will use u is equal to trace phi square to parameterize our vacua. Okay, so that was the other thing that we talked about last time. We've got this moduli space of vacua. Then we talked about the physics as a function of the moduli space. Remember that if we're far away in vacuum space, phi has an expectation value. Okay, if we're far away there, then since trace phi squared is non-zero, some component of phi has a non-zero expectation value. Okay, so this breaks the gauge symmetry. Phi was in the adjoint, which is like a vector of SO3. So what, if you turn on one vector of SO3, what is SO3 broken down to? It's broken down to U1, the rotations around that direction. Okay, so the physics of this vacuum, of most of these vacua, at least when we're far away, is that of spontaneous symmetry breaking from SU2 down to U1. So we expect the low energy theory to be that of a U1 photon, okay, and its n equals 2 counterparts. So we've got this picture of a whole plane labeled by this trace phi square. We're calling it a plane, but we may change that in a while. Labeled by this u is equal to trace phi square. We've got this picture of these vacua, and at least when we're far away, far compared to what? Well, compared to the strong coupling scale, which we call lambda q CD. Okay, so if we're in this u plane, lambda q CD square. At least when we're far away compared to lambda q CD square, the physics is that of spontaneous symmetry broken and effectively is weakly coupled, because the gauge coupling has not had the time to run as we go down. This is clear, right? And right at the end of the last class, I described the quantitative question we would be addressing. Right at the end of the last class, I described the quantitative question we would be addressing. The question went this way. For a U1 gauge theory, for n equals, which is n equals 2, we discussed how the most general n equals 2 Lagrangian took the form phi bar, now no e to the power minus v because it's uncharged. So phi bar and then del f by del phi, okay, plus del 2f by del phi square times w alpha w alpha. This is d4 theta, this is d2 theta. Maybe at some point in these lectures, we will go back and look at this algebra more carefully to see how that comes about in maybe two or three different ways. But for now, let's move on. Okay, let's accept this and move on. but f is a function of phi. So what is f? F is equal to some function of phi. Okay, so good. So motivated by Diksha's question, let's ask what function of phi would give us the free U1 theory? Just the free theory. Okay, as Diksha just said, f is equal to phi square. Is equal to alpha times phi square. Let's say maybe we'll put tau by 2 phi square. The tau is some constant. Now what do we get? We get the free theory, which is phi bar. Let's, yeah. There's some constant out here, but phi bar phi, okay, d for theta, okay, plus d plus tau w alpha. There's an imaginary part, right? Okay, so there's that plus complex conjugate, or minus complex conjugate, whatever. Okay, so that would give you the usual free theory. But now we're allowing for much more general possibilities. The more general possibility is for f being any holomorphic function of phi. Okay, good. So our goal, the goal we've set ourselves is the following. The goal we've set ourselves is to compute this f of phi as a function of where we are in moduli space. Okay, this is our goal. This gives in general, no, it will not be higher derivative. It will be 2 derivative, but with a non-trivial metric. Let's look at this a little more. Let's look at the kinetic term that comes out of this. You remember that in general our theory of n equals 1 was we wrote down k of phi bar and we did d for theta. And we got that the metric was obtained, so that the kinetic term was del k by del phi I del phi bar j. Okay, and then del mu phi I del mu phi j, phi bar j. This was our general kinetic term that followed from such a scalar potential. Okay, so this quantity here we can or will call the metric on the moduli space of scalars. Okay, so this quantity here is the metric, so let's compute the metric in terms of f. Note that this is just a special case of that, so it gives rise to 2 derivatives. Okay, gives rise to 2 derivatives, but it gives rise to a very special metric. Let's compute the metric. Okay, in this case of something of this form, the scalar potential is just phi bar times del f by del phi. Okay, so if we, in general, if we had phi bar I del f by del phi I, if we had something like this, we take the derivative with respect to phi bar j, that gives us this. Okay, and the derivative with respect to this gives us a second derivative of this. In the particular case of interest, there's only one phi. Okay, so the metric, this metric here is del 2 by del f del phi square. Del 2 by del phi square d mu phi d mu. So the metric on moduli space is just the second derivative of a holomorphic function. Del. What? How did this come about? It came by substituting k is equal to phi bar del f by del phi. Now let's take a derivative with respect to phi bar, that gives del f by del phi, and then take a derivative with respect to phi, gives del 2 by del phi square. That's just using this formula with this form of the metric of the Kähler potential. Yeah, that came from n equals 2 supersymmetry. The fact that we got this form of the Lagrangian in terms of a single holomorphic function, that was a consequence of n equals 2 supersymmetry. We reviewed it briefly last class with this extra constraint in superspace. That's one way of saying where it came from. Another way would be just to take this Lagrangian and check that it's n equals 2 supersymmetric. Check that in components it gives rise to n equals 2 supersymmetry. This is not a very hard exercise, but you can do. Okay? Okay, great. So this is not a very weird kind of action. It's just an action with the usual kind of kinetic term for scalars with a given metric on moduli space. And it's also got, well, what's the interpretation of this guy? Well, the interpretation of that guy is that it has an effective coupling constant. Okay? The interpretation of that guy is that it has an effective coupling constant. This is clear, right? Because what the role of tau is being played by del 2f by del phi square. So the coupling constant now is a function of where you are, where on this moduli space you are, rather than being a constant. Okay? Great. Great. So now, for the first time, we're going to get semi-classical. Okay? For the first time, we're going to get semi-classical. We're going to ask, suppose we're at very large values of u, but not infinity. Okay? What can we say then about the about this function f? Okay, so how do we answer this question? Well, I'm going to give you one answer to this, one way of answering this question based on this U1 symmetry. And then once we get the answer, we will find another way of thinking of it sort of more intuitively.
Large value of
Vacuum expectation value. So the theory should be weakly coupled there, so there should be no barrier to finding the physics, right? Okay, so what I'm going to try to do is to ask, at one loop, once we include not just classical effects. Classically, of course, f is whatever we, in the UV theory, we start with some value for this f function. This f function in the UV theory is an f function for now all three fields, right? Because phi is an adjoint of SU2. So it's phi 1, phi 2, phi 3 with SU2 indices. We know exactly what that f function is. And then we just put in our expectation value, integrate out, meaning set to 0 the W bosons, and we get what we get. Okay, so classically that would effectively set the coupling constant of this U1 field to whatever it was in the UV. It's a simple exercise that you can do, just a classical exercise. Okay? Because the other parts of the gauge field become massive. Some funny stuff happens there, but the U1 that you're looking at is precisely the part that is unaffected by this vacuum expectation value. So its action is exactly what you started with. Okay? So classically we would have some classically tau would be f would be like tau phi square by 2. Now we're going to ask, how is this action corrected to one loop? Okay? Now in order to answer this question, we remember two things. A, anomalies are visible at one loop. And B, this U1 symmetry that we discussed last time and we reviewed again this time, the one that was anomalous, is anomalous. Okay? So if we compute the one loop effective action of our theory, then this effective action should not have, this U1 should not be a symmetry of the theory. And instead, the change in the action, if we perform such a U1 transformation, should be exactly what we predict from the anomaly equation. Right? So if we perform the following variable change, phi, this is not the superfield, the scalar component, goes to e to the power 2I alpha. Psi goes to e to the power I alpha. Okay, and lambda goes to e to the power minus I alpha. No, plus I alpha. Plus I alpha. Okay, we perform this U1 transformation. The change in the action delta S should equal 8 alpha times trace F wedge F. Okay, this is a constraint on our one loop effective action that we just know to be true. Okay, so we're going to try to write down this one loop effective action, a one loop effective action that has this property. Now look, so we want some one loop effective action. We want some one loop effective action that will leave this unchanged, but will change this by this amount when we make that change, because that's the thing that gives rise to the F wedge F. Is this clear? Okay. Let's try to come up with a term that will do the job. Okay. Claim if you take zeta phi square log of phi by lambda, or maybe phi squared by lambda squared. This will have the right property. If we choose a one loop correction to F1, this is the one loop, is of this form, we will get what we want. Why? First, let's compute. First, let's see what happens when we compute. First, let's just compute del f by del phi and del f by del 2 phi. Okay, so del f by del phi with this zeta some constant, which we'll fix in a while.
So this term is correction to original tau phi square.
Yes, this was the classical part. The one loop correction we're claiming has to take this form with a number whose value we will be able to compute. The epsilon, the zeta. Okay, so del y. So let's compute del f by del phi. Okay, so there are two terms. There's zeta. There's 2 zeta phi log phi squared by lambda squared. Let me call it log phi by lambda. It's irritating. Okay, plus zeta phi squared zeta phi. Okay, let me call it log, and then we will get 2 zeta. Okay, and del 2f by del phi squared, we differentiate again. Okay, del 2f by del phi squared. So one term is hit this guy, so we get 2 zeta log phi squared by lambda squared. What am I doing? Sorry. Let's. Sorry. Let me just keep. I'm sorry. Not that any of this matters, but let me keep my factors of 2 straight. When I differentiated this, I got a 2, and I got a log. When I differentiated this, I didn't get. I just got phi. Okay. No phi, right? Because just log here and 2. I keep changing it. I'm sorry. Okay. Yeah. Okay. And now when I take this second guy, one term is this. The second term is when I differentiate this, so that's 2 zeta. And the third term is when I differentiate this, so that's zeta. Okay, so when I do this, I get 3 zeta. Okay, so del 2f by del phi square is equal to 3 zeta plus 2 zeta. This one is not there?
Did you wrote phi square or phi?
Phi square here. Here there's just phi.
That is the answer. Oh, you are writing that. Okay.
Log of phi by lambda. Okay. Now you see, what is this term? Just some constant that can be absorbed into some shift of this tau, changing some constant. Changing the effective constant doesn't change any of the symmetries of the theory. But what about this guy here? What about this guy? Under our symmetry, phi went to phi plus e to the power 2I alpha. So under this symmetry, the change in this is 4 zeta I alpha.
In the power.
In the power, but there was a log. So just downstairs. Okay? The 4 came because 2 zeta and then 4 alpha. Now, you see, when we have a tau, the real part produces f square. When we put tau in here. Real part produces f square, where imaginary part, which is the I theta, couples to f wedge f. Okay? So what this does is induce a shift in this tau, which is purely imaginary. So it's a shift in theta. Okay? And it's a shift which is 4 zeta alpha. But this is exactly the kind of thing we wanted. But we wanted that shift in appropriate units to be 8 alpha. So if we choose zeta appropriately and keep our normalizations all straight, we will get it to work, but only with a given value of zeta. Okay? And now I will trust that Seiberg and Witten have done their normalizations correct, and I will quote you the value. Okay, so what we've concluded is that f0, which is f classical, was equal to tau, what I call phi, they call A for some reason. I mean, I suppose they were the, huh?
Scalar part they call it.
Scalar part they call it, fine. So let me write it as a function of the scalar part. I'm just using their notation so that you can compare with that paper. Okay, this was the classical part, that's what we wrote here. Okay, and then the one loop part was plus a square by 2 pi log of a squared by lambda. A squared by lambda. Just a minute. There's some factor of I am looking at. Is tau? Okay. I'm sorry, so they have an I here, okay, which seemed to invalidate our previous argument, but their tau was equal to, with an I in the real part, 4 pi by g square plus theta by 2 pi. So with these conventions, the shift here has an I and another I, so it's real, and it's exactly changing theta. Okay?
Sorry, so what we did here was to guess f, which will change under the action of phi, will change the theta term exactly what we want.
We'll change the theta term exactly as we want it to happen.
Based on the z8.
Given that we knew exactly how things should, exactly how things should transform. Okay? And, basically there weren't too many options. Because we know that we want this thing to change by a log. So we know that we want the second derivative, we know that we want it to change linearly in alpha. So we know that the second derivative of this thing has to have a log. Could have a constant, but could have a log. Okay? And had to have a log with the right coefficient. And then we could integrate that to get what f had to be. Okay? So the fact that we know how it had to transform under symmetries almost completely fixes f. Almost completely fixes f. Why almost completely? Anyone? What? Constant terms. Okay, so one or two constant terms, that's fine. But there was a more serious almost. If this was it, we wouldn't be studying this paper, because then we would have finished the exercise now.
There can be functions when taking derivative is 0.
Okay, yeah. What yeah, how does that logic go? How does this logic go? Okay. Okay, let me give you the logic as, okay, let me give you a bit of logic and then let me give you a story and then we'll compare with what I just said. Suppose instead of trying to match the anomaly, I demanded that the preserved symmetry, namely the Z8 symmetry, be a symmetry of the theory. Okay? Then this log will do the job, because its transformation, its coefficient has been chosen so that its transformation is its transformation has the factor of 8. So if I do pi is equal to alpha is equal to 2 pi n by 8, all it will do is shift theta by an integer amount, which doesn't change the theory. What? So what is this? This has been designed to do the following. With this f, we have that that theta shifts by 8 alpha. That's by design. We wanted this. Good. Yes, theta goes to theta plus 8 alpha. Okay. What? Minus. Maybe it's a minus. Yeah, possibly minus. Okay. Theta goes to theta plus minus 8 alpha. And if alpha is 2 pi by 8 times some integer, that is some integer shift in theta. Okay, which doesn't change the theory. But for this remaining Z8 symmetry, I mean for this Z8 symmetry, can you write down any other term, okay, that is also invariant under Z8? Clearly, a to the power 4n, alpha n a to the power 4n. This will do, because a has charge 2 under the Z8.
Yeah.
So these will all be neutral. Okay, so under the Z8, under this Z8, this guy is invariant, but so would terms like this be. Okay, so you might suspect that perhaps we would be allowed to correct this f of a, but of course only by terms that preserve all the symmetries of the theory. Okay, of course only by terms that preserve the symmetries of the theory, and the terms that preserve the symmetry of the symmetries of the theory are things like this, because there's Z8 invariant. Now there is something, we'll come back. There's something about the logic that is a little confusing here, but let us come back to that. I mean, the thing that's confusing is this. If you took everything I've said, put it together, it would appear that this guy, that the transformation of our effective action under this shift has a term that is not quite wait, I probably saying it wrong. Just give me. It's probably something stupid. Sorry. Yeah. It's fine. You see, these guys are instant-on contributions.
This looks like a superpotential, but you initially said that we should not write any n equal to 2 invariant superpotential.
No, this is for f of a.
Oh, okay. I thought this is not in the Lagrange.
This is where I'm saying we're looking at this function f of a. And we're looking at possible corrections for this f of a. Okay, now you see this correction here. Okay, this correction, okay, of course it's correct, yeah. Sorry, so one thing that we saw was an explicit alpha f wedge f that we reproduced. But you see, imagine that we've got corrections to our superpotential that come from integrating out instantons. Instanton effects produce corrections to our superpotential. Now, instantons themselves are backgrounds that have a non-zero f wedge f. Okay, so one instanton background carries f wedge f charge equals 1, and so should violate this charge by 8 alpha. So an n instanton background carries instanton charge f wedge f is equal to n, and so should violate this charge by 8n alpha. But that's precisely what this does, because under a goes to e to the power 2I alpha a, this charge is violated by 8n alpha. So we're seeing that this u1 is violated by f wedge f, both the explicit ones that's in front of our eyes. Really, this is the preserved u1, the f wedge f of the unbroken u1, as well as the f wedge f of all the broken stuff, the massive gauge bosons that we've integrated out. Right? Remember that del mu j mu was equal to trace f wedge f for the full SU2 gauge field. So there are two sources of variation, two sources of the right hand side. One is the stuff that comes from the massive guys, f wedge f contribution of the massive guys. One is the f wedge f contribution of the massless guys. Massless guys we have an integrator out there in front of our eyes. So an f wedge f in the massless field should then that was that log. But the massive guys we have integrated out. Okay? So in sectors where we've integrated them out, where F_F was non-zero, those sectors should violate this charge conservation by a precise amount. And we see that this is exactly what's happening here. Okay? So there are two ways of getting the most general form of the answer. First, by looking at how everything should transform under the anomalous U1. And then we can also check to see that once we do this, is everything a symmetric under the preserved Z8. Okay? These are two equivalent ways of looking at the problem. Oh, not quite equivalent. The first one's a little more powerful, but the second one's got much of the information and it's a good check. Okay? So we have concluded that the most general superpotential must take the form sum over n alpha n a to the power 4n, this plus this plus this. The most general F, not superpotential, I say prepotential. Most general prepotential must take the form of this form. What is left to determine is all these alpha n's. Okay? So semi-classical analysis has done a good job for us. Right? Semi-classical analysis has done a good job. It's computed this one loop term with a coefficient that is known exactly. But it was just semi-classics. Okay? There's an infinite number of numbers we have still to determine. This is our program.
Why do you call it semi-classical if we are computing based on
Semi-classical because what we used here was information that came from one loop. I mean, we knew exactly what that coefficient was. The fact that that had to be violated by 8 units of alpha.
Yeah, but that we know from exact symmetry.
We know from exact symmetries, I agree. But this term was a one loop diagram. So we could just compute it if you wanted, right? In the same way that we could compute an anomaly by computing one loop, same computation. The problem about these terms is if you try to compute them, you would have to compute instanton effective actions with lots of instantons. Because alphas are undetermined, yes. Loop calculations, simple loop calculations are not telling us what alpha is. Yes, exactly, as Sunil said. We've got the form, but we don't know what the alphas are. Actually, since Seiberg and Witten, people have done extremely impressive localization type calculations to directly compute the contribution to the prepotential from instantons and have summed up the answer to reproduce the answer we're going to see in class. Directly by honest instanton calculations. Okay, very impressive. Nekrasov is one of the key players in this program. This is not what we're going to do because we're going to get the answer, by much more beautiful methods than a direct computation. Okay, but now perhaps you have a better sense of what the program is. We need to find these f's. And this is the unknown data in some sense. You will see as we go along that even the problem will get a little modified as we go on. Okay, so I'm sorry, and this should have been minus 4n. All n is equal to 1 to infinity, because when a went to infinity, we have to recover the classical answer. Okay, so this is what we get classically. This is what we get semi-classically. This should be good at large E. Okay, but as we come nearer and nearer in, we can get more and more serious corrections. Okay, now you can ask how do powers work out? Okay, and powers work out because we've got lambda QCD by 8 to the 4 to the power n. We have a mass scale in the problem. Okay, and the fact that this term goes like lambda QCD to the power 4n can also be used to confirm that it's an instant term, because this term goes like e to the power minus, an instant term goes like e to the power minus 1 over whatever 8 pi square, 8 pi g square, whatever it is. And then g squared is written in terms of lambda QCD via the formulas of the beta function. Okay, and so then that gives us a particular power of lambda QCD, and in this case, one instanton turns out to be 4. All these, of course, the same thing. Okay, so that's another way of confirming that this is an instanton contribution. Okay, before we proceed, you may have the following worry. Okay, you may have the worry you may have is this. Okay, great. This thing here correctly generates the change we need in this term. But look at del f by del phi, not del 2f by del phi square. By the way, you understand that this shift is over and above classical, right? These W alphas have precisely the opposite transformation under the symmetry that theta has, because of the lambda. So that without this shift, it would have been invariant. Right? Were this to be a constant, this term in the action is invariant, because the gluinos have been given mass charge 1 under the symmetry. It exactly cancels the theta thing, like what we did for the Seibert thing. Right? Would have been a symmetry had it not been for the fact that there's this shift. This you understand, right? Okay, so now you might wonder, well, what about this guy? We made such a big deal of this fellow. What about this guy? What about its transformation under alpha? Okay, so let's look at this guy. So we've got phi bar times, so this term in this action is 2 zeta phi bar phi log of phi bar phi log of phi. Yeah, now having said that, what about it? Is there an imaginary part? Just 1 minute. Yeah, there's an imaginary part here. Sorry, this whole action came with an imaginary part. And why does that imaginary part work? Just if it was real. I'm getting confused about real versus imaginary. This quantity under this, this guy and this guy transformations cancel each other. That's the usual story. This guy picks up a 2 zeta, then 2I alpha, phi bar phi. There is an I where? Zeta itself is imaginary. Yeah. There you go. So put the zeta inside. Yeah. So exactly. So we've got the zeta, and then there's an imaginary, and then there's an imaginary part. So this real part goes away. Okay. So in the transformation here, in the transformation for this guy, it's unaffected by the shift, as we should expect. Okay. So fine. So this exhausts the information of what semi-classical dynamics will do. Okay, by the way, there's yet another way of thinking of this term here. Okay, the other way of thinking of this term goes as follows. Look, that what we're getting here is some effective value of tau. So tau effective is equal to tau plus, let's say, log of a squared by lambda squared. I, good. Remember that tau was equal to I by g squared. So what this is telling us is that, that in this tau, we're replacing g by an effective g. And this effective g, as Diksha said, is what we should expect. Because you see, remember where this is valid. This is valid at very large A. There, the running of the coupling constant is weak and appropriately captured by one loop. So shifts in G are logarithmic with a beta function coefficient. Okay? And you check the beta function coefficient, it's the right one. The beta function coefficient for this. So this, what this does here is capture the running of the effective gauge coupling. You see, the U1, the effective gauge coupling of the U1 theory is the effective gauge coupling of the SU2 theory, but at what scale? SU2 theory gauge coupling runs, right? So it's the effective gauge coupling of the SU2 theory at the scale of breaking, because that's where the running stops. Okay? So we input G at scale breaking, and that gives us this tau effect. At lambda cutoff equals A, exactly. Yeah, so this thing here is equal to, so is equal to I by G squared A. Have I got the constants right behind G squared? I've written this down before. 4 pi. I by 4 pi G squared A is equal to I by 4 pi G naught squared bare coupling, okay, plus I log A squared by lambda squared by pi, I suppose. Minus 2 pi I took because there was this tau by 2. That was this pi. And I did it wrong. You said so tau I substituted by I by G squared. Why?
Shift in tau is I times ln A square by lambda square 1 by pi.
Yes.
And that is multiplied by.
And tau is I by G squared, 4 pi by G squared. Okay? So this tells you what G squared of A should be.
G is always real.
G is always real, yes. This tells you what G squared of A should be. Okay? And you can check that this is exactly what the beta function equation gives you. Okay? So great. So that's another way of thinking of what we got from semi-classics. Okay. Fine. So now we seem like we're well set. We seem like we've got a well-defined problem. We understand its contours. We have to go about solving it. Most of us with this kind of stuff, I think I could have done, right? All of you could have done. What comes next is the incredible bit, right? It's like, as you will see, it's really incredible. Okay, but before proceeding to where we're going, we should notice that there is a puzzle. Please.
Why are we sure that there are no higher loop effects? So we took one loop effect.
Yes.
And then we directly went into taking the instant on continuation.
Yes.
Are we using a renormalization theorem or something?
You could say that, but I think the logic makes it sort of clear. You see, because the anomaly is exactly del mu j mu is 8 times f wedge f. Okay, and that is an exact statement. Now, therefore, every violation of this current has to come from f wedge f. Okay? Hang on. First, we are looking at an effective action. So there is also an f wedge f in our effective action. So one violation could be shifting of theta of our effective action. But every other source of violation, no matter what loop you do, as long as it doesn't involve non-zero f wedge f, that is, as long as it doesn't involve an instanton, cannot change this. Okay? So my claim is the following, that the only effect, so let's separate this into two parts. Those that violate the current, those that violate our symmetry, and those that those that violate the symmetry in a power law way, and those that violate it in a way that saturates the anomaly. Okay? The only thing, the only term that violates, the only term you can write down for the potential that violates it in a way that saturates the anomaly with the f wedge f of the u1 that is in front of us is this, is whatever this.
Could be a little compound which doesn't contribute to anomaly, but still it's there in
Okay, but how do we write down some term that doesn't contribute to the anomaly?
You're saying del square f is
Multiplying this. So if we take a power series expansion, every term in the power series will contribute to the anomaly, because A transforms under the power series, under the anomaly. Remember, it's holomorphic. So it cannot be that you take A and A bar and they cancel each other. Okay? So there's nothing that does not contribute to the anomaly. But there are terms that could have contributed to the anomaly, because they came from f wedge f of the stuff we've integrated out. Those are the instantons. So it's clear from this that no power law corrections of that higher loop stuff, of that massive stuff, by integrating out those guys at loop order, could have produced something that could have changed this, because anything it would have done would have changed the anomaly. More precisely, Diksha, as you know, in perturbation theory, what you would get is nth order in perturbation theory, you would get log a to the power n. It will be impossible for that not to contribute to the anomaly, right? It will contribute in some very funny way. In perturbation theory, you never get powers of A. Okay, but instantons nicely give you powers of A. Precisely in a way that violate the symmetry, but in a way that you expect it to be violated. Because the right hand side of the del mu j mu had not just the f wedge f from u1, but also the f wedge f from the su2. Is this okay? Okay, excellent. So, now we are set. We're getting into the interesting part of the paper. But before that, there is a puzzle that I want to introduce you to. And the puzzle goes as follows. Okay. So Seiberg and Witten asked the following question. We want some f of A. Okay? And remember that the metric on moduli space for the scalars was del 2f by del A square. Similarly, the term that comes, the effective coupling constant for the f mu nu is del 2f by del A square. Remember that. Now, the fact that this is the case tells us that we will have a kinetic term which is of the form del mu A bar. F is holomorphic. Okay? F is holomorphic. There's some imaginary part here. F is holomorphic. Okay? But something we know something about this del 2f by del a squared. The imaginary part of it, because of the imaginary part there, must always be a positive number. Because if there's any value of a, if any value of u, let's say, where it turns out to be negative, then our scalar field has a kinetic term of the wrong side. If our scalar field has a kinetic term of the wrong side, all hell breaks loose. We can increase energy by crumpling up space. We can decrease energy by crumpling up space. We can decrease energy by oscillating fast in time. Unitarity is violated. All hell breaks loose. Just something that we don't want to get into. Okay? So either the theory is not well defined at some values of this expectation value, which I suppose is possible, maybe. But if we're optimistic, the theory is nice and somehow has a good vacuum everywhere. If we assume that's the case, then this quantity here always has to have a positive imaginary part. You can make a similar argument from the gauge coupling, because the coefficient of 1 by g square, the effect of 1 by g square is del 2f by del. Yeah? And if this guy goes negative anywhere, it's like a theory with negative charge square. Charges will pop out of the vacuum, crazy stuff will happen. We don't want to get there. Okay? So we've got this function here that has to have imaginary part that is always positive. Okay? On the other hand, this function we thought was defined on the complex u plane. And it's sort of strange that it can have an imaginary part that is always positive, because it's a holomorphic function. And if we look at a holomorphic function, its imaginary part can nowhere have a minimum.
Yes.
Imaginary part can have saddles, but never minimum. So how can it be that we have a function that is not unbounded from below in imaginary part on the whole complex plane, even though the thing is holomorphic? There is a boundary, that's right, and on the boundary we're good, right, because we know what our f is. So we can take our del 2f by del 2 square. An imaginary part, that extra imaginary part that comes from the log, is some very bounded thing. On the boundary we're fine. In the middle, it should nowhere go negative. Okay? But if it's nowhere negative, then there's some place where it's a minimum.
But there was this symmetry, right?
There is a bound.
A going to minus a symmetry.
What?
There was this Z2 symmetry.
No, but we're in the u plane. Let's say that we're parameterizing it by trace u square. The boundary is at infinity. So I've got
Then you have problem.
what? Yeah,
The boundary is
at infinity, right?
yeah.
But we've got the whole complex plane in front of us. We've got to have a holomorphic function that has this property.
But if you have a boundary,
If you have a finite boundary, then the minimum could be reached at the boundary.
yeah, exactly. Yeah, like
Yes.
the boundary, then you can.
Yes, yes, yes. Okay. Yeah. Right. So the lesson they draw from this fact is the following. It cannot be that this f is a globally well-defined thing. Now what does that mean? You see, the analogy is when you're dealing with like a gauge theory. Let me make an analogous argument. An vaguely analogous argument. The analogous argument might be that if I'm on a sphere, I can, in a U1 gauge theory, I can carry no flux. Okay? Let me make the argument. Suppose my sphere, I've got this S2, and I draw a Wilson line across somewhere, let's say the equator. Then I use Stokes' theorem to say that B dot ds on this side is A dot dl. And then I use Stokes' theorem to say B dot ds on that side is A dot dl, but with a minus sign because the orientation is flipped. And therefore B dot ds over the whole sphere is 0. And it sounds like a great theorem. Beautiful, very easy to prove, except it's not right. And the reason it's not right is that there is no A field everywhere on the sphere. You can make an A field in one patch and an A field in another patch. And the A field on first patch can be related to the A field in the second patch by a gauge transformation. By a gauge transformation that winds around this, the circle. And then if we run this argument again, A1 dot dl is B dot ds. A2 dot dl is the other thing. But A1 dot dl integrated minus A2 dot dl is this winding number. And therefore the B dot, the flux in the sphere is not 0, but it's an integer which is the winding number of this gauge transformation. Okay?
A1 and A2 are differ
By on a
But it's bigger than just local gauge transformation.
what, say again? A1 and A2 on some patch. Say I take a strip. On the southern part I've got A1, but including up to here. On the northern part I've got A2, but up to here. Now on the strip they're both defined. And the rule is that when they're both defined, they don't have to agree, but they have to agree up to a gauge transformation. Now on a strip, a gauge transformation is interesting. Because it's a gauge transformation is what? It's a map from where you are to U1. But where you are, because we've got a strip, has non-contractible S1. So it's a map from S1 to S1. And that has a winding. So this gauge transformation can wind. And precisely that winding is the difference between the B dot ds and B dot ds. Okay? So precisely that winding tells you that it's not true that you cannot have a flux on the sphere, but what is true is that the flux on the sphere has to be an integer. Okay, and then you can get the quantization units from this also. In units of 2 pi, it's got to be an integer. Okay? Excellent. Okay, so in units of 2 pi, because that gauge transformation winds by 2 pi. Because the gauge parameter comes back to itself up to 2 pi.
It's like d theta.
Exactly, d theta. Right. Okay. So the idea, the vague idea, is maybe something like this is going on here.
So does that take some information about the topology of the space on which we are trying to define this?
Yeah. You will see there will be a torus that plays a role in the game. You will see as we go along. Yes, that's a very good question, and there'll be a clear answer by the end. Okay. But the first question, Diksha, you had a question.
Sorry, I thought that this F was valid only if the spontaneous symmetry breaking happened before lambda.
Okay, yes.
So this F is not well defined everywhere.
Okay. Yeah. Right. What we are assuming is that this formalism is valid everywhere. You see, even if lambda QCD, if we have like a half lambda QCD, we've got this thing. It feels like gauge symmetry is broken down to U1, right? So it feels like there should be a massless U1 gauge field everywhere except possibly at potential singularities where new massless fields appear.
So yes, if SU2 was not broken.
If SU2 was not broken, but you see, because trace U squared has an expectation value, you would have to have a situation where trace U squared has an expectation value
Which is very less small than lambda.
very small compared to lambda QCD. Yeah, okay, good. So Diksha's question is this. Diksha's question is, could it be that there's some region where this picture breaks down? If that happens, then there is a region which should become singular from this point of view. Okay? And that never happens in holomorphic functions. You have singularities at points, but not on lines. You see, because everything is depending on u but not on u bar. So for instance, let's take an example. Okay, it's true you could have a cut. What could happen is that you go from one sheet to the next. That could happen on a line like this. But a singularity is like 1 over z to the power n, right? This doesn't happen on lines. Okay? So holomorphicity makes this sound extremely unlikely. Okay? What could happen and what will happen is that there will be points where things go funny. This we already knew even classically. A equals 0 was a point where the massive SU2 gauge bosons, were not massive anymore. Okay? And it could be that there are other such points. In fact, we will find some. And it could be that there is some sense, and we will see, that there are cuts between these points. This could happen. But the singularities should be codimension too. Because holomorphicity, that's how holomorphic singularities are. Okay? Yeah. Okay, excellent. Now, so where were we? Were we discussing? Was there a point we were making before this? This analogy, thank you. Yes. So I was talking about this analogy. Now, what is the analog of that here? What is the analog of having one gauge and another gauge and within patches? Okay. Now, in a gauge theory, physics was invariant under gauge transformations. That's why you could have these patches, right? Because you could have one patch and then another patch where the physics was the same on the overlap, but up to a gauge transformation. What could the analog be here? Large gauge transformations. Tau goes to, yeah, right. So, you mean SL2Z gauge transformations. That's correct. But what is the physics of that? Okay, so we want some operation under which physics is invariant. But that is not a triviality on our presentation. Okay, just like going from one patch to another was an operation under which physics was invariant, but it was not a triviality of the presentation. The A field changed. A field on one is not the same as the A field on the other, but they both gave rise to the same physics. Okay? So what we are searching for is something like that. But quantum field theory is a path integral. We're doing a path integral with this action. So what are the operations we can do on a path integral without changing the physics? Well, it's basically change of variables, or more sophisticatedly, dualities. So let me explain what I mean by this. Okay? So now we're coming to the key physics of the Seiberg-Witten paper. Okay? The key physics of the Seiberg-Witten paper is that of duality of U1 gauge theories. So this is something we mentioned before, and I've given you the 3-dimensional. In class we even discussed the 3-dimensional version of it, if you remember. That the theory of U1 gauge boson in 3 dimensions, same as that of a compact boson. Okay? But there is a 4-dimensional version of this, which is that the theory of a U1 boson is the same as the theory of a U1 boson, but in a non-trivial way. Let's look at that. suppose I was trying to do a path integral, and let me, unlike my usual style or my usual incompetence, let me try to keep track of numbers this time. Okay, let's see if I can. Okay, so let me write trace f mu nu 1 by 4 g squared e to the power minus. Let's say that this is the action that we wish to study, where f mu nu was the field strength of a U1 gauge field. Okay. Now, the path integral we are studying is this quantity, right? It's dA mu exponential of minus 1 by 4 g squared f mu nu 4x, where f mu nu was equal to d mu a nu minus d mu a mu. Of course, this is very familiar. Okay, now I want to write this path integral in another language. So look at this writing of it. Let me do d f mu nu. Let me use f mu nu as the basic integration variables, and then write exponent. What? An antisymmetric field. That's all. Okay, minus 1 by g squared f mu nu f mu nu. I've not changed anything. Okay, I've not changed anything, but then I want to put in the fact that f mu nu was d mu. Now, one way of saying that is that f mu nu obeys the Bianchi identity. In fact, this is a better way of saying it that it's d mu a mu plus d nu a nu. Because you see, as we just discussed, in a situation like on the sphere or on a torus, there is no A field for which it's d mu a nu minus d mu n. But the Bianchi identity is always true. So let me just impose the Bianchi identity. That is the real path integral of the gauge field. Telling you that the Bianchi identity is always obeyed. So let me put an I, and I'll call this A dual. A dual alpha, and then del beta f theta phi epsilon alpha beta theta phi, and the requirement that we get the factors of 2 right will kill us, but okay, fine.
So in 3D, since it was a 3-form way.
Yes, it was a scalar. You went to 4? 4g squared. See, I've already missed. And whether you want a 4 factorial or not here, that will kill us. But okay, let's take it as it comes. Okay.
This is a lower dimensional Bianchi.
No, it's the full Bianchi identity.
df equals to 0.
Right? Because I put, this A dual is such a cumbersome, let me call it B alpha. The equation of motion of B alpha is del beta f theta phi is equal to 0 with this epsilon. So any antisymmetrized derivatives of f are 0. That's the Bianchi identity. Okay? Moreover, I've put it with an I. So the path integral, when I do this and I integrate over real values of B, this is not a classical manipulation, it's exact within the path integral. Because the integral over B imposes Bianchi identity as a delta function. And then up to some measure factors which are independent of fields. And I'm not keeping track of. This is just exact in the path integral. Okay? So this is a writing, in fact a more accurate writing of the gauge theory path integral than say.
That the Bianchi identity imposes form for everything to be
Locally.
Yeah. Okay, so then
And that's all we need.
yeah,
In a simply connected manifold, it ensures that it's always, but you know, we only require, see, even in a simply connected manifold, like the sphere, like S2 or S3. Well, let's take torus. Oh, it's simply, yeah, you're right. We need an S1 or something like that.
Yeah.
You're right. Yeah, no, simply connected manifold, fine.
Some theorem,
Right, some theorem. You're right. Right. That it would be, yeah, exactly. That can be written d of A.
Second path integral is equal to the first path integral?
Yes, the second path integral is same as the first path integral, up to some constant normalization factor independent of fields. How do we know this? We know this because this integral enforces the Bianchi identity. The Bianchi identity tells us that at least locally this is of this form. And actually this first path integral was inaccurately written. What?
How did the Bianchi identity go from second, how did the Bianchi identity ensure that the second path integral?
It's how does it do it? Because you see, if we have that df is equal to 0, then f is equal to dA up to some global business. Right? So df is equal to 0 tells us f is dA, but f is dA is the statement.
closed exact.
Closed exact. There's some distance between them, but where there is that distance, this is the correct one, because this is precisely this patchwise business. We don't need f is equal to dA globally. We only need it locally, and that is the same thing as saying all we need is that the Bianchi identity is satisfied. That is the only real thing we need.
Since f and a are linear, we don't have to worry about the
Jacobian, right? Some constant which we forget about. Okay? Now at the next step, we take this theory and say, now let's be adventurous. Let's do the integral in the opposite order. So if we integrate out b, we get back the theory we wanted. Or really we get back the more precise version of the theory we wanted. Okay? On the other hand, if we integrate out f, remember f here is just some field. It appears quadratically. So we can integrate it out. Okay? We integrate out f. Then what will we get? It will be quadratic in B. And yeah, it will be exactly the same thing. Now let's first get the signs. When we complete the square of this,
I think after total derivative, you can, these shapes are now anticipated.
yeah, first thing is I'll put this d here.
Yeah, exactly.
That's what Schumann wanted. Huh? Now because there's the epsilon, it is antisymmetric. Okay, now I'm losing, despite my promise, I'm losing various factors of 2. Okay. Let's keep signs at least. Okay. See, now we take this thing square. That is needed to complete the square.
But it's minus a, so it will always be minus. Like it's I or minus, it will always give you minus.
It will always give you minus, right? So what we had is minus a square plus minus doesn't matter, as you said, IBA.
Yeah, it will minus b square.
Okay, and so when we complete the square, this is let's make it 2IBA. So this is minus of a. Let's put a plus just for fun. 2IB, no, IB, the whole thing square. This is what we want to do. So the extra term we got was a plus b square. The extra term we got was minus b square. And so the term we have to add to cancel it is minus b square. Okay, so we're going to have to add a minus b square term. Okay, we're going to have to add a minus b square term. That minus b square term is clearly the square of this anti-symmetrized Okay, so clearly you're going to get a minus. Yeah, there you go. 4g squared, g squared clearly comes up. Okay, so we'll get fb mu nu fb mu nu by g squared, and then there's a question of a number. Okay, I'm sorry, it's just too painful to work it out. we get this by 4.
Yeah,
I think we get it by 4.
yeah, because there is beta phi and epsilon alpha beta theta base, that will be the factor of half.
Yeah, great. Okay, just you can work this out. You will get this with a factor of 4. Okay. Now, this looks like we have said. This looks like we have deduced that a U1 theory with a coupling constant G is the same as a U1 theory with coupling constant 1 over G with this new variable change. However, some of you, I can see Diksha already are beginning to say this, are saying that this makes no sense because your theory was quadratic. So G had no meaning. We can always remove any G, make any G 1 by a field redefinition. So what does G goes to 1 by G mean? Okay, and in this case, the answer is that it's not quite quadratic because of flux quantization. Okay, it's not quite quadratic because of flux quantization. So let me explain that. Okay, you see, G has meaning because we are defining our theory to be this form where fluxes of F are quantized in units of 2 pi. If we scale G out, it will change the quantization rule for F. Another way of saying it is that we are defining G to be F of this form, where the gauge transformation is A mu goes to A mu plus B mu phi, where phi has periodicity 2 pi. If we rescale A, we will rescale the periodicity of phi. So if we always insist that our gauge field has periodicity 2 pi, which is the same as saying that fluxes are quantized in units of 2 pi, remember that argument that came from the periodicity of the gauge field. Okay, if we insist on saying that, okay, then G has meaning. So now that we have declared our rule was that in the original theory, gauge transformations were periodic modulo 2 pi, or equivalently fluxes were quantized in units of 2 pi. Now the question now has meaning. So we want to know whether we've achieved this change of variable, this result in the convention in which FB also has fluxes quantized in units of 2 pi. If that is true, then this has meaning, right? Then G goes to 1 by G. It's meaning. It's not some convention. Is this clear? Yes. Okay. So now let us imagine. Okay. Let us take the original path integral. Okay, let us take this original path integral and put in this quantization of flux. Okay, so suppose we were on some non-trivial manifold, let's say a torus, let's say a 4 torus. Say we're working on a T4. Okay, on 2 cycles of that T4, this original flux F, its integral over the torus, okay, was necessarily quantized. Okay, so what we can do is to work, these quantization sectors are different topological sectors in field space. So we can work in a given quantization sector. Let's say that its flux units on that torus is m, and let the gauge field be whatever, some winding configuration corresponding to this M, this flux configuration M, plus a fluctuation gauge field that is topologically trivial. Okay? That fluctuating gauge field, so suppose we were doing that, for instance, in this integral. Okay? This is our gauge field here. The gauge field that will go into here. Okay? We're doing the path integral over these B's. We put in the fact that B is integrally quantized. Okay? Let's say we put that in. So what that means is we're doing the path integral over all the trivial topological sectors, that's integral over B, plus the sum over fluxes. Because in each sector, we're doing a path integral over all the trivial sector fields. Because the most general configuration in non-trivial sector is one configuration with the non-trivial flux, plus trivial sector fluctuations. It's the trivial sector path integral that produces the Bianchi identity. But the sum over fluxes is still left over. The sum over fluxes tells you that this guy here has a non-trivial flux. But look at this integral here. So now,
You want to write it as total derivative?
it's even simpler. So suppose we write this part here as this guy here can be decomposed into zero mode and its Fourier modes. Fourier modes, we're looking to see what happens when we look at the flux sectors. Flux sectors here are constants. Constant times Fourier mode gives 0 upon integration. So the only thing that clicks is constant times constant. Okay? Now here we had d for x. We had d for x, and then let's look at the term which was, for instance, f12 b34. We have to keep various factors of 2. But there's a term like this. f12 is quantized. Okay? So let's take this d for x was dx1, dx2, dx3, dx4. We'll write this as dx1, dx2, f12 times dx3, dx4, b34. Both were constants, so we can put whatever integral we want. But this guy was just this flux, and this guy was the other flux. Okay, so this is f new, and this is f old. Okay, so if we demand that f new takes all integer values, and we sum over those integers, that gives us a quantization condition on f old using the formula that e to the power I n a, when n is an integer, gives you quantizations in the units of a being 2 pi. Okay? So if we demand that this thing is, normal quantized, that gives us a constraint on the fluxes of the original theory. And you do this properly, the constraint is integers with integers. I would have to keep track of various factors of 2. Okay? You can already see that there's no g coming in here, right? Clearly the constraint will be maybe with 2 pi, maybe with 1, that you have to get straight, but no g. So clearly we're getting g squared goes to 1 by g squared. And maybe even...
As you say, the g can be also absorbed.
G cannot, actually, maybe maybe this one has a 4 pi squared. Right. It could be that this number was wrong, that this was 4 pi squared. Because, I think it's tau goes to 1 over tau in the conventions where you have 4 pi by g squared. Yeah, I think 4 pi by g squared goes to 1 over 4 pi by g squared. Yeah, so maybe we get a 1 over 16 pi squared here. This number you'll have to look up. Okay, 4 pi by g squared. And that makes sense because we need some 2 pi's somewhere here. Okay, so I'm sorry, I thought I would do it with numbers, but it's too much of a pain. But you understand, right? You understand the point? The point is that when we do the sum over fluxes for this guy, and with that, we wanted, because this was a normal gauge field, we were writing in terms of B, the gauge field. So we had to put in the sum over fluxes. That tells you that despite this being a regular antisymmetric gauge field, the only terms that contribute are those in which the zero modes of it are quantized. So quantization of the first gauge field, or the new gauge field, implies quantization of fluxes of the old gauge field. Okay? And you do it properly, you get this G goes to 1 over G squared goes to 1 over G squared, perhaps with the 4 pi. Is this clear? Notice that you get the same physics and even the same action, but the variables are very different. So the equation of motion that you solve by completing the square here tells you that, up to some G squared, it will tell you that 1 over G squared factors of order 1 are not accurate. F mu nu is equal to star of B mu nu. So what was F12 in one gauge field is F34 in the other. In particular, as Karthik said, if we take F01, which is what we think of as electric field in the one direction, it maps to F23, which is magnetic field in the dual theory. So it's electromagnetic duality where you're exchanging electric and magnetic field. Okay? So you want to insert an electric field on the first side. It's the same as inserting a magnetic field on the second side. Okay? Now, there are various other things, various other exercises you can try. One of which is the following. Okay? One of which is the following. Suppose I have a charged particle coupling to the first gauge field. So I do the path integral in the presence of a Wilson line, let's say, with a charged particle, some charge. Exercise. Take that Wilson line, make it infinite in R4. Do the duality transform in the presence of that Wilson line. And see what it becomes on the other side. Okay? This is an insertion in the path integral. Now in the presence of that insertion, we do this duality map again. Okay? What you will find is that you will be forced to do the path integral in the background of a solution where there is a Dirac magnetic monopole. What? The Toft operator. Yeah, the Toft operator was a bit more sophisticated. It's one of these things that performed one of these gauge transformations in the center of the gauge group for SUN theories. This is even simpler. It's just a path integral in the presence of a singularity. The singular behavior is a specification of f as it comes out. Try this little exercise and see it. It's a fun exercise. Okay, you will see how electric and magnetic charges thereby are getting mapped to each other. Okay, roughly speaking, it goes this way. Roughly speaking, it goes this way. Let's start on this side, because this side is where we have the B field available to us. Here it would be hard to couple a charge field, because charge field couples to A, and we don't have an A. Okay, but here we had on this side here we have the B field. So we can start with putting an I, E, B, or INB, let's say, nicely, an integer, okay, over some world line. Okay, so now the whole action includes this INB as well as all this other stuff. Now when we integrate out B, we've changed the Bianchi identity for F. Bianchi identity doesn't give us F is equal to 0, but it gives us F is equal and that's a monopole. Okay, but you can work this out in detail. Okay, so this is how electromagnetic duality works in 4 dimensions for U1 theory. It's trivial because it's quadratic, more or less. All trivial, but we can see it in front of our eyes. So it's a nice thing. What is the relevance of this discussion to the paper of Seiberg and Mittel? Please. Yeah. Good. It would be like G is equal to 4 pi. G squared is equal to 4 pi. Would be self-dual. Is there something special about it? Probably. You know, you can ask the same question about n equals 4 Yang-Mills theory, which has a more interesting duality. Again, under the same G square goes to 1 over G square. Again, there's a self-dual point. What is special about it? People have conjectured, almost certainly there's something special about it. I don't know what it is. I don't think anyone has made a clear statement. Here, everything's quite so trivial, you can work out whatever you want. Okay, I don't think you'll find anything very interesting. But in the case of n equals 4 Yang-Mills, it's a very interesting question. People have conjectured this, that in the case of the of this bootstrap, when they do bootstrap with supersymmetric operators, people have tried to do it with n equals 4 Yang-Mills and found some sort of kinky regions, and suggested that these kinks are the self-dual point. It's almost certainly a very special case. What? Ising model you're talking about? Yes. Yes. In the Ising model. So now how does that go? This is Ising model in 1 plus 0 plus 1 dimensions? 1 plus 1 dimensions? 1 plus 1. 1 plus 1 dimensions. Yeah. That has the strong coupling, weak coupling duality. Yes. There, as you say, there is a phase transition, and if there is one phase transition and you have a G goes to 1 by G duality, it has to be at 1. In n equals 4 Yang-Mills, we don't believe there is a phase transition of the theory as a function of coupling. In fact, it would be strange because it's holomorphic. So the free energy would be is a holomorphic function of tau. So where would that phase transition be? You can always go around it, right? You need a wall. Similarly, in response to Diksha's question, right? It's hard to get these line type singularities which are holomorphic. Okay, yeah, there's almost certainly something special. I wonder whether that is a solvable point. Could it be that it's hard to solve n equals 4 Yang-Mills exactly at finite n, except at that point? Feels like a good conjecture. Somehow feels like something like that might be true, right? Because there's a new symmetry in this theorem. Apart from n equals 4 Yang-Mills, supersymmetry, there's now this symmetry of duality. Because now this is not relating one theory to another theory. Now it's relating the same theory to itself. So maybe the combined symmetry of superconformal invariance plus this duality is strong enough to allow us to solve this theorem. People must have tried something. You should look up. I don't really know. But sounds like, I don't think there's been any sharp progress. I would know. I would have heard of it. I don't think there's been anything clear said about it. Sounds like a great question. Yeah. Why is Bianchi identity non-zero being momentum? See, what is Bianchi identity when we write it in terms of magnetic field? It's del I Bi is equal to 0. That there is no charge, magnetic charge. The fact that that is modified tells you there is a magnetic charge. Right? Okay, so I just say the last thing and then we'll quit for the day. Do you know Basu? He was telling me yesterday that he was remembering my field theory course. He was saying, I don't know I don't know if you realize how exhausting we found it. He was saying that, we used to go on for 2 hours, and I thought I was understanding everything you said, but when I came out, I couldn't reconstruct. It was just too exhausting, so I shouldn't do that. I mean, you guys may not even know. I'm old enough and he's young enough, so I've taught him. Okay. Anyway, so, with that bit of input, I'm resolved not to go more than 10 minutes over time in classes. So we'll stop soon, but let me just say this one last thing. I've gone on for the last 20 minutes about this duality, right? And we will in the next class review the n equals 1 version of this duality, or even an n equals 2 version of this duality. Okay? Now, you might ask, what is the relevance of this whole discussion to what Seiberg and Witten are talking about? And the relevance goes as follows. Look, the analogy is between, if you have 2 different path integrals that produce the same field theory, then that's like having 2 different gauges that produce the same physics. Right? Because anything you want to, it's the same theory. Anything you want to compute in one, you can compute in the other. Okay? So the thing that Seiberg and Witten suggest is the following. Suppose there is that you cannot cover all of moduli space in one description, in one kind of path integral description. Suppose that's the case. Suppose what happens is that in any patch, there are patches in moduli space where one kind of path integral works. And then there's another patch where another path integral works, maybe in terms of the dual field. Okay? And there's an overlapping region in which both work. That's all you need for the continuity of physics. We need that physics is continuous, things are holomorphic, all of that. All that is needed. But this would be sufficient to guarantee, just like if in a gauge theory you've got one patch where we've got one gauge field, we're working on one gauge, another patch where we're working on another gauge, and there's some region of overlap. This is all that is needed. Okay? So maybe what's happening is that moduli space is continuous, smooth. But in order to see the smoothness, you have to cover it in patches of descriptions. Now, the effective action that they were talking about was an effective action for a U1 gauge field. I will show you next class that this little exercise we did with duality has an n equals 1, really an n equals 2 counterpart. Okay? So, what the suggestion is that there is no good path integral description of the physics in one set of fields over all of moduli space. To cover the whole of moduli space, we need to go into patches. In one patch, we've got a good description in one set of fields. Another patch, we've got a good description in another set of fields. And so on. Perhaps that's how it works. Okay? And we are going to actually try to make this assumption, proceed, and see what comes out of it. Okay?
Define the region where you're talking about.
You'll have to see. You have to see. You know, the way that we are going to actually, the way that it will go is as follows. We will have a moduli space with some punctures. The punctures are singularities where this U1 description doesn't work. Okay? In some sense, there's a puncture at infinity, as you will see, as I will explain. But really the important punctures, there will be two. In the classical theory there's one. That's where gauge bosons become massless. Okay? Now, the idea is that as you go around punctures, because as in gauge theories, you need something non-contractible to be interesting. Because if you had a contractible region, then you can just shrink. So nothing interesting can happen. Okay? You need something non-contractible for it. So as you go around a puncture, you're going to be forced to change description. Now, you see, because the only interesting thing is to do with these going around. The real question is, one way of wording the question is this. Are you familiar with this? When you're studying gauge theory on a torus, let's say, or on a circle, let's say on a torus, one way of thinking of it is put patches. That's how a mathematician will tell you to do it, right? You put a patch here, a patch here, a patch here, maybe 3 patches for a circle. Or maybe 2 patches for a circle. Okay, whatever. But often for a physicist, it's much easier to say the following. There's just one patch. But as you go from 1.0 to 2 pi, your boundary conditions are that all your fields have not come back to themselves, but come back to themselves up to a gauge transformation. This is equivalent, right, to that other thing. Because that coming back to yourself up to a gauge transformation is essentially that gauge transformation, non-trivial gauge transformation that's done in that overlapping patch. Okay? This is often how we think. It's sort of, for practical purposes, easier than putting patches. Okay? So similarly, the question that these guys will ask, so one of monodromy, as you go around a singularity and you come back, your effective description should have come back to itself up to a duality transformation. Okay? So what we will have to, that is the condition we will put on our physics, that things are not periodic, but are periodic up to duality transformations. Okay? Now, I may keep saying this, but sorry, just one thing I wanted to say that I should have said at the beginning. You see, so in this little discussion we had, I kept track only of g squared. But actually I should have been keeping track of 4 pi by g squared plus theta by 2 pi, something like this. The whole complete constant. Now, there is an obvious symmetry of this theory, which is theta goes to theta plus 1. That is an obvious symmetry. We have also argued for a symmetry which is g squared goes to 1 over g squared, or tau goes to 1 over tau. Okay? If you put these two symmetries together, you get, if I call this whole thing tau, theta goes to theta plus 1 is tau goes to tau plus 1. And the g squared goes to 1 over g squared is tau goes to minus I by tau. What? Theta goes to theta plus 2 pi is tau goes to tau plus 1. Okay? Now, you can look at the group that is generated by these two transformations. SL2Z, that is SL2Z, right? So, the full duality group consists of a trivial element, which is theta goes to theta plus 2 pi. To see that that was an invariance of our theory, we didn't need to do anything. It was obvious. Didn't need to make a change in description. And a non-trivial element. This tau goes to minus 1 over tau. Very much like when you are looking at tori. There's the trivial thing of tau goes to tau plus 1, just changing cycles. And the slightly less trivial thing of interchanging. Tau goes to minus I by tau. Very much like that. Okay, so the full duality group here is not just the Z2 thing, it's this SL2Z. Okay? And when we go around the singularities, we will be able to come back to ourselves up to any element of SL2Z. Okay? This is the constraint we will put on our theory, and then try to solve it, always subject to the condition that we always have positive positive coupling constant. The fact that if we did not do this duality business, we got no solution, subjective positivity, was already telling us it's a highly constrained problem. So if we allow for this duality business, perhaps we can just solve it, find a solution uniquely. That's the hope. We will try to see that next.